Sure. Good day once again, ladies and gentlemen, and welcome back to the Inside Science Theory. Today, I want us to go through this past paper as part of our consolidation videos on chemical equilibrium. Um, so I sourced this paper from the November 2015 exam. Okay, November 2015 exam. Okay, so they say an unknown gas of X2 is sealed in a container and it is allowed to form X3 at 300 degrees Celsius. As you can see, X2 forms X3. Notice how they're using X because like they said, it is an unknown gas. I have a feeling there was going to be a question that's going to ask you to determine which gas this actually is, but I doubt there will be. The reaction reaches equilibrium according to the following balanced equation. So this is the equation. Um, How will the rate of formation of X3 compare to the rate of formation of X2 at equilibrium? Write down higher than, lower than, equal to. Now, this is a tricky question. What does it ask you? It's asking you how the rate of formation of the reactant, which is this guy, X, sorry, how the rate of formation of X3, which is the product, will compare to the rate of formation of X2, which is the reactant. It's basically asking you what the definition of equilibrium is. What is equilibrium? Dynamic. What is chemical equilibrium? It is equilibrium where the rate of the forward reaction is equal to the rate of the reverse reaction. So when they ask me about how the rate of formation of this guy will compare to that guy, that means it will be equal to, by definition, dynamic equilibrium where the rate of the forward is equal to the rate of the reactant. So in this particular case, the final answer here should be equal to. So I just highlight when it comes to these things, guys. So your answer there is equal to. Right. So now they say now the reaction mixture is analyzed at regular time intervals, and the results obtained are shown in the table below. So I have time from 0, 2, 4, 6, 8, 10. So this time, as you can see, they said regular time intervals. So it's in the time increases in seconds at intervals of 2 seconds each time. So I have the concentration of X2, which is zero point 0.4. It decreases to zero point 0.2. It increases, it then so this concentration is actually decreasing, right? The concentration of X2 actually decreases over time. And then they say the amount of this, the mole of this thing is from 0 to 2.6. So this concentration is actually increasing. So for this one, the concentration is decreasing, and this one, the concentration is increasing, which only makes sense. I mean, you are using the reactants to form the product, so this will then increase. Okay, now they say calculate the equilibrium constant Kc for this reaction. Calculate the equilibrium constant Kc for this reaction at 300 degrees Celsius. I do not know why this is 4 marks. This is a weird marker location, especially when it comes to the Kc calculation. Okay. Let's see. So that's 6.2. So the equilibrium constant Kc is the concentration of the products over the concentration of the reactants. And that will then be equal to, what is the concentration of the products? The concentration of the products. So the concentration of the, what is the product? X3. So I think in this case you can use any. I mean, at the end of the day, as time progresses, you can use. I mean, you can choose to use any. You can use time at 10 seconds, 8 seconds, 6 seconds, but you must use corresponding values. I mean, obviously, you wouldn't want to use this because if that's the product, and then zero divided by this would mean the case is zero, which I mean, and I don't think they really would want you to use that one. But let's see, what would you guys like to take? Which one would you guys like to use? Okay, I heard someone say they would like to use 8 seconds. Let's see. Um, hmm, yeah, let's see. So that's gonna be 8 seconds. It's gonna be the concentration of the product, which is x3, that's 0.226, and over the reactant, which is x2, and that's 0.06. Consider these guys. Do not forget the stoichiometric coefficient. So for x2, that's squared, and then for this one, that's cubed. And then the final answer will then be, let's see. So that's 0.226 squared over 0.06 cubed gives me a value of 236. That is a large Kc value. Oh my God. So that is 236.46 to two decimals. Ratio, no units. Okay. And that's what you have. That's the Kc value. Um, so let's try something different. Let's see if you would have obtained the same results if we used, I don't know, let's go try 4 seconds. 4 seconds would be 0.213 over 0.08, and I would square this, and I would square that and cube this. This would then be 0.213 squared over 0.08 cubed, 0.08 cubed, 0.213, 0.08. Well, you don't get the same answer actually. So that would be a reason. There's, I mean, there obviously is a reason for that. Could be because of the fact that if you think about it, well, notice how from 6 seconds all the way to 10 seconds, the concentration of both the reactant and the products are the same. So if you know that the concentration of both the reactants and the products are the same, you should know that you are actually at equilibrium, right? And that's what we associate Kc with. Hence we call it the equilibrium constant, basically. Okay, let's see. They now say 6.3. More X3 is now added to the container. Let's write down this reaction, guys. You know, this is the only way we'll answer these questions. So that's 3x2. This produces, my gosh, what's going on? This produces 2x3. So they're saying more x3 is now added, meaning they increase this concentration of x3. How does equilibrium react again, guys? To favor to counteract this disturbance, it would favor the reverse reaction, right? And as a result, the concentration of this guy would decrease and this guy would increase. Okay, so how will this change affect the amount of x2? Write down increase, decrease, or remain the same. What did you say? We've already established that the answer here would be increases. The amount of x2, remember? They're asking about the amount of x2. The amount of x2 would increase. Now we're going to take what we've done here and convert it into Le Chatelet's principle. Like I said, they always ask this question. I mean, think about it. If this is the people from 2015 and they ask this question, why would they stop asking it in 2025 and 2026? But in essence, they could stop. I mean, not necessarily stop, but just give you guys a break. Maybe not ask about it in the prelims or something. But it's always just there. So 6.3.2. So you need to write this in terms of the Chatelet's principle. So you need to say um, Well, you just need to talk about an increase in the concentration. So increasing the concentration, increasing the concentration of X3. Guys, this is just me writing it like this. Please write in full when you're in the exam. So increasing the concentration, right, affects equilibrium. Affects equilibrium. We don't have to add this first point though. So the system will favor the reaction, right? The system will favor the reaction that will counteract the disturbance, that will counteract the disturbance, right? Thus, the reverse reaction is favored. Tell us why this thing increased. Thus, the reverse reaction is favored. Therefore, X2 concentration increases. Thus, the reverse reaction is favored. Therefore, X2 concentration increases. And there you have it. That's your answer, right? So there's some points I've added that you shouldn't have. In fact, just have all the points. I mean, it just makes sense, you know. Okay, so let's see what we have here. Guess what I want? Okay. Oh, and that then brings us to the end of this question, and that's that. But it does have a continuation, however. Yeah, this is the continuation of that question. This graph that you see here. This is where the question continues. Let me just make this bigger so you guys can see. I think this should be big enough. Okay, now they say the curves on the set of axes below was obtained from the results in the table on page 10. So this was page 10. Um, and then they say, how does the rate of the forward reaction compare to the rate of the reverse reaction at T1? Write down higher than, lower than, or equal to. So let's think about it. So let's look at this diagram. So notice how this diagram has from page 10. So it's a diagram for these results. Okay, I just need to make sense of that. Okay. So notice how there's something that is getting used up. The concentration decreases. That would obviously be your X2 because that's your product. Remember that X2 is used to form X3. And then this would be your X3. So what you must understand is now at this point here, I want you to think about it. So at this point here, time t1, I want you to focus on this point here, time t1. Okay, let me make it use a different color. This is green. I know I'm using green lately. Let's just remove green. Let's use, I don't know, blue. Okay, this is nice. Okay, so at the point t1, now you must remember. Now the question says, how does the rate of the forward reaction compare to the rate of the reverse reaction? What is the rate of the forward reaction? That is the reaction when X2 is forming X3. That's the forward reaction. So what is the rate of the forward reaction? Now remember that at the point T2, sorry, T1, we do not assume that the reaction is that the system is at equilibrium, right? So what will it be here? Will it be higher than, lower than, or equal to? Let's think about it. So now we've understood what we mean when we say the reaction, when we say the forward reaction. That's when X2 is starting to form into X3. So obviously, notice how the amount of X3 starts to gradually increase over time, right? Because it's now you're starting to form X3, so the amount increases over time. So as a result, the rate of the forward reaction, which is the rate of formation of X3, must be higher than the rate of the reverse reaction. Because in this way, the forward reaction in this diagram, if you notice something with the forward reaction is when we are forming X3. So as a result, that would then lead to the rate of the forward reaction, the rate of formation of X3 to be higher than the rate of formation of X2. That would obviously be the reverse reactant, the reverse reaction. So if the question was like, how does the rate of the reverse compare to that of the forward? Your answer would have been lower than, right? Because if you look at this reaction is basically the reaction of formation of X3. The graph, rather. The graph is indicating the formation of X3, and that is the forward reaction. Hence, we say the answer here for the forward reaction will then be to be higher than. Why? Because the forward reaction is the formation where we are, is the reaction where we are forming X3. The rate of the formation of X3 is what they're basically asking about. Will the rate of formation of X3 be higher than, lower than, or that, or equal to the one of the reverse reaction? And obviously, it should be higher than, right? Okay. And then the reaction is now repeated at 300 degree, oh my gosh, 400 degrees Celsius. The curves indicate, I've been using the light blue highlighter. The curves indicated by the dotted lines below were obtained at this temperature. So notice how for the solid lines the temperature was 300, and for the dashed line the reaction was 400 degrees Celsius. Is the forward reaction endo or exothermic? Fully explain how you got to your answer. Ooh, okay. This one is a crazy one. This one is a crazy one. Okay, let's think about it. So look at these graphs, guys. Notice how. I want you to notice something. I want to see something here. Okay, I've seen what I need to see. Right, anyway, is the forward reaction exothermic or endothermic? Explain how you arrived at your answer. Now let's look at this. Think about it. Let's look at the temperatures. Remember the initial temperature was 300 and now the temperature is 400. Therefore, in essence, there was an increase in the temperature. And what does it mean? When I increase the temperature, what information does that give me? That tells me that I favor the endothermic reaction. I'm not saying that's the answer. Remember, just breaking it down. It favors the endothermic reaction. That's what an increase in the temperature does. It favors the endothermic reaction. So now you need to think about it. If the concentration, remember now they are asking about the forward reaction. If the concentration over time, this is still X2, and this one here is still X3. If the concentration of X2 decreases and the concentration of X3 increases, what does that mean? Let's think about it. The concentration of X2 decreases and that of X3 increases. What does that mean? So let me write down the reaction once again. That is going to be X2 to give me X3. So if this guy's concentration increases, what does it mean? This means that you had to favor the forward reaction. And automatically, once you favor the forward reaction, what happened? Once you have favored the forward reaction, think about the fact that that means either heat had to be increased or heat had to be decreased. But since we've already established that there was an increase in the temperature, that then tells us that heat had then to be increased. And if we increase the heat, the system must counteract the disturbance by favoring the forward reaction, right? So if you think about it, okay, so let's think about it. So, um, let's look at the graph. Let's try and understand what goes on in the graph. So notice something. At 300 degrees Celsius, this is what I had for x2, right? Notice this graph here. That was the graph for x2. My gosh. Okay, but that was the graph for x2. And then what happens? At 300 degrees Celsius, notice something. So notice the tail at 300. The tail is here, the tail for x2. and then the tail for x3 was there, right? But notice the tail for x2 now is above the first one, and then for x3 it is below. So notice how when the temperature was increased, let's think about it. When the temperature was increased, what happened? When the temperature was increased, the amount of x3 decreased from that point there to this point here. And the amount of x2 increased from that point there to that point over there. So if you put this in reaction form to try and understand whether the forward reaction was exothermic or endothermic, let's think about it. So let's see what would happen here. Well, if it happens that I've established now, ladies and gentlemen, that the concentration of this guy must decrease, what would lead to that? Obviously, we'd need to favor the reverse reaction, right? We would need to favor the reverse reaction. Oh my gosh, the reverse reaction so as to decrease the concentration of X3. As you can see on the graph, when the temperature increased, the concentration of X3 decreased, right? We're not saying that we are not gonna um we're not gonna have any X3 at the end of the day. No, just saying the concentration of it will decrease when you increase the temperature. And why would that be? That would be because we favored the reverse reaction, thus increasing this guy. And as you can see, he actually increased, and this one decreased. Now, the question is, when you relate this to temperature and heat, what would it mean? If you increase the temperature, you're increasing the heat. That means you had increased the heat on the reactant side. And as a result, that is why equilibrium chose to favor the reverse reaction. And remember, what does it mean when we have when we have heat on the reactant side? What does it mean? It tells you that you have delta H less than 0. Therefore, your answer here should be exothermic. And there you have it. Your answer there should be exothermic. So trying to make sense of such things, guys. I almost made a little blunder there. So I had to think about it for a moment. Okay. Now, fully explain how you arrived at. Oh, okay. Now we already got 1 mark. So we just need to explain for 3 marks. Let's see. Point number one. Let's talk about what we see here. Um, Notice how on the graph, guys, I'm going to use square brackets. Please write in full if you have such questions in the exam. The concentration of X3 decreases. And the concentration of X2 increases. The concentration of X3 decreases and the concentration of X2 increases, right? What does that mean? As a result, um, thus, oh my gosh, I wrote deuce. Thus, that tells me that the only way that's true is if and only if the reverse reaction is favored. Since the reverse reaction was favored, what does that tell us? Since thus the reverse reaction was favored, therefore the reverse reaction, no, before we get to this point, remember we need to link. Now I want you to think, I want to include this point. I want to integrate this point inside my answer. So I'm going to say thus the reverse reaction was favored, right? An increase in the temperature since an increase in the temperature, since an increase in the temperature favors an endothermic reaction, since an increase in the temperature favors an endothermic reaction, the reverse reaction was endothermic. The reverse reaction was endothermic. And as a result, you can then say, therefore, the forward reaction is exothermic. So notice how I'm linking, guys. Notice the link. I tell them that the concentration of X3 decreases and the one of X2 increases. I then it obviously it makes the marker ask himself or herself, why do you say that? Well, sorry, X the concentration of X3 decreases and that of X2 increases. So what does that mean? That tells me that the reverse reaction is favored, right? And tell me more. So how does that link to the forward reaction being exothermic? Well, if an increase in the temperature favors an endothermic reaction, that means the reverse reaction is endothermic, and if the reverse is endothermic, automatically the forward reaction must be exothermic. You see how you answer these questions, guys? You must make sense in your answer. Don't just jump from this point and get to that point and jump. No, don't jump like that, guys. So notice how. Let me say it again. What did I start by saying? I started by saying the concentration of X3 decreases and the concentration of X2 increases. Okay, so why? What does that mean? This means that the reverse reaction is favored, right? Because X2 is a product and X3 is the reactant. Since the increase in temperature favors an endothermic reaction, the reverse reaction was endothermic. Okay, so if the reverse is endothermic, automatically the forward reaction is exothermic. Simple as that. Okay, now they say, redraw this curve in your answer book in the same set of axes. This looks like this actually is the Maxwell-Boltzmann distribution curve. It shows the number of particles against kinetic energy at 300 degrees Celsius. So redraw this graph in your book. On the same set of axes, sketch the curve that will be attained at 400 degrees Celsius. So remember from rates of reactions, we had said that if you increase the temperature on the Maxwell-Boltzmann distribution curve, then that would obviously decrease the peak of the graph and then widen the graph itself. So number of particles, and then we have kinetic energy here. So the initial graph was something like this. Now, if I introduce 400 degrees Celsius, that means I would have something like this. And there we go. So this is 400 degrees Celsius, and this is then going to be 300 degrees Celsius. And that is the end of this question, ladies and gentlemen. Full 15 marks. I really hope this was very helpful. The next time we meet, we will be doing a completely different topic. But for now, I shall see you in the next.